Okay, so welcome back to another video. So here we have an integral transformation identity we would like to verify, and that is to show that for a and b strictly greater than 0, we have that the improper integral from 0 to infinity of f of a times x minus b over x quantity squared dx is equal to 1 over a multiplied by the improper integral from 0 to infinity of f of x squared dx. So this transformation has a special name. This is known as the Cauchy-Schlömilch transformation. And it's actually a special case of a theorem known as the Glasser's-Masters theorem, which helps explain how a certain broad class of substitutions can simplify certain integrals over the entire real line. So we're not going to go too much into that theorem for one, because we just want to verify that the left-hand side equals to the right-hand side. So be prepared to hear me say a lot with dummy variables and u-substitutions, because that's all how we're actually going to prove the following of the left-hand side is equal to the right-hand side. So that's actually more of the direct approach that we're actually going to do from here. So with that, let's actually just get started. So let's suppose that for we do a u-sub, so we let u equals b divided by a times x. So we actually want to, when we do a new substitution in terms of a new variable, we actually want to put in back for x, so we want to solve that by its own. But by doing so, we have that x is equal to b divided by a times u. So that's nice that we can actually differentiate both sides for dx and replace that with a new differential. So we have that dx is equal to negative b divided by a times u squared and then du. And so here, now we can actually put this back in. So I'm actually going to call this the left-hand side of our transformation identity. We're going to call this capital A. So capital A is going to be written as, the same as our given. So once with that, now let's actually plug in our new substitution. So for one, we have to calculate our new bounds. When we have infinity, we plug this back in for x, then that means u is going to approach 0. And if we plug 0, then that means u is going to approach in positive infinity. So with that, we have our new bounds in terms of u. Then we plug in back the new substitution. So that means what's nice is that everything will now it's going to be b divided by u minus a times u, then quantity square. Then put this back with our new differential. So this is actually going to be negative b divided by au squared and then du. And so taking a couple steps ahead further, what I'm going to do is, for now, we know that since this is an even degree, we can actually just interchange these, and then the equality will still preserve the same, thankfully. And another thing is that we can actually interchange the bounds, so that'll become negative. Then that negative over here will also cancel each other out. And because we have a b and an a and they're constants, I'll also factor that outside of our integral. So now everything, doing all this, we're going to have b divided by a, then multiply with the integral from 0 to infinity of f of a times u, then subtract b divided by u, then square, and then we're going to have du then divided by u squared. Now what I'm going to do here is that now let's actually perform yet another u substitution. We're actually going to call this variable v though. So let's actually get to that. We suppose that we're going to let v equals a times u and then subtract b divided by u. So if we differentiate both sides, we're going to have that dv is going to equal to a. So let me actually put a parentheses just to distinguish this. And then now I'll change that to a positive. So a plus b divided by u squared and then multiplied by du. And so now next thing I'm going to do is, well, we actually took one step ahead. So because what's we're really supposed to do here is, the clever trick is that we're going to actually multiply 2a to our given. So the way we're going to do this is that we have, so this is 2a. Then I'm actually going to add the sum of our given integral from our identity, and I'm going to add this with the new substitution that we actually performed from the very beginning. And so right here, so we're going to have our original integral that was given. And keep in mind that I'm actually just keeping this in terms of u in that world. So we're still in the u world. Again, it's a dummy variable, so that's okay. Then add this with our substitution back over here. So this is plus b divided by a, then multiply with 0 to infinity of f of a times u, then subtract b divided by u and then quantity square, and then multiply with du and then divided by u squared. And so from here, we can see that we can factor out the integral. So what that comes down to is that we have 1 divided by a, then we multiply with the integral from 0 to infinity of our integrand over here. So that's f of a times u and then b divided by u and then quantity square. Then we can actually put this back in as the factor of a and then plus b divided by u square, and then put this back in for du. And this is nice that because we took this one step ahead, we actually did the differential for our new u substitution for v, so we can actually perform this, get this out of the way, and so now we actually have a new rewritten integral in terms of v. So this is 1 divided by a, and then now again calculate our new bounds is that we have infinity for u, so that means this is going to be infinity, then that's going to approach 0, so then this is still positive infinity. We have a 0, so 0, and then that's actually going to approach infinity, so that means that's actually going to be negative infinity over here, and then this is f of v squared and then dv, replacing that substitution back over here. So that's great. So how do we proceed forward from here? Well, it looks like we're actually one step closer, since we actually have an integrand similar to here. We have a 1 over a, but our bounds are different because we have the interval of the entire real line, but meanwhile this is just the positive half real line. So we're actually going to have to get a little bit creative here, and what I can do is we'll actually split this as a sum dealing with the first of the positive half, and then add this with the negative half of the real line. So what this comes down to is that we'll have 1 over a, then divided from the integral from 0 to infinity of f of v squared then dv. We add this with 1 over a, then now dealing with the negative half of the real line, so negative infinity to 0 of f of v squared and then dv. And so we're going to take into our focus into this specific integrand over here. So I think you can see where we're going with this. So it's nice to know that we know that v squared, it actually can be rewritten as negative v quantity square. So what's nice is that we just replace this back in, and then I can actually do another, u substitution for the third time, and then we'll call this w. So we'll let w equals negative v, perform the differential, so we have dw is equal to negative dv, and so that will be that negative dw is equal to positive dv. And then now put this back into the integral, so I'll actually write it like this first. So back to the original, we have that this is negative infinity to 0. Put this back as negative v quantity and then square. Then we'll actually perform the new substitution back in for here. So what we get here is this is 1 over a, then we have our new bound, so we plug in 0 for v, so that's actually going to be 0 for w, and plug in negative infinity, then that'll be a positive infinity over here. So this will be f of w squared, and then plug in the dv, new substitution, so that'll be negative dw. We can simplify this even further. For 1, we flip the bounds of integration, that'll become a negative. That cancels out that negative over there too, so that's positive. So we have 1 over a multiply from 0 to infinity of f of w squared and then dw. And so that's nice that we can actually do a little bit of a substitution of this replacement over here. So now overall we have that so far 2a is equal to 1 over a. We're just rewriting that same thing over here. 1 over a times the integral from 0 to infinity of f of v squared, then dv. Then again, dummy variable, we're going to put this back in for v for that new substitution back here. So this is again, that's supposed to be 1 over a back here as well. 1 over a, then the integral from 0 to infinity of f of v squared, then dv. Add these up together, they're the same thing. So we have that this is 2 divided by a of the integral from 0 to infinity of f of v squared dv. Then all it's left we have to do now is just divide 2 to both sides, and so we actually just complete our verification proof to say that a is indeed equal to 1 divided by a multiplied by the integral from 0 to infinity. Replace this back with a dummy variable for x, so f of x squared and then dx. And just like that, that actually completes our verification proof. Simple as that, with a couple use substitution. This is actually all just elementary calculus techniques that we learned, that we just follow through with a bit of a creative tricks here and there. And so just like that, we have complete the verification of the Cauchy-Schlömilch transformation identity, just like that. The special case of the Masters-Glasser's theorem. So there we have it. So yeah, that's pretty cool if you ask me.